Brussels last. Just found it yesterday by chance on my computer. Forgot that this movie exists, so it is not included into the talk. But this is one of the clusters from these multi-dark simulations. So what you see is on the left-hand side the gas evolution, on the right-hand side the stellar evolution, and then this cluster is forming. It's a zoom simulation, zoomed on one of the clusters of the multi-dark box, the multi-dark boxes in 1 gigaparsec box. I don't remember how big the resolution was in this case. So, shall we start? So this is, I think, I stopped with looking into this movie which goes through one of the multi-dark boxes, and this was basically the first one which we were running for Bolshoi. Bolshoi is the largest one which we were running with the hard code, with this adaptive refinement code. Anatoly. Bolshoi is Russian, means large, big. There's a Bolshoi theater in Moscow, the largest theater of Russia. And this is in WM5, 1048 cube simulation, 150 articles. There's a big Bolshoi web page at the University of Santa Cruz. So we started to do different things with that. This gives you an impression what we were talking about before. So this is the full box, 250 megaparsec, and then we zoom in into a cluster. And now the size is only 4 megaparsecs, a relatively small part of this original box. And you get an idea why we need this high resolution, namely because we want, if we have a cluster of galaxies, like here, a big cluster of galaxies, we want to resolve the inner structure of this cluster in the full box. And this is necessary if you want to calculate, for example, the correlation function of galaxies or such things, because then you need to know also if you have big halos which consist of many galaxies, you need to know where the position of these galaxies is. In particular, if you're in data, the merging tree or whatever, what you need if you want to calculate, you want to put real galaxies in the dark matter simulation. I mean, you can do it also if you don't have the resolution, but if you don't have the resolution, you would need to put galaxies in more or less random places in such a cluster. So this is a general table, a general overview about the simulations we have performed in this project. So it goes from 4 megaparsec down to 250, from 4 gigaparsec down to 250 megaparsec with a different resolution. And the most interesting in the moment is this one. This is a 400 megaparsec simulation with almost 4,000 cube particles, which has a really high resolution. And for this simulation, we started we started to construct a merger tree. And the next step will be to put galaxies into this simulation with the Galacticus semi-analytical model. So we are running in the moment Galacticus over the small multi-dark, over the 400 into 1 gigaparsec simulation, and then we intend to put these galaxies into the dark matter halos, and finally the galaxies will be part of the database, the company database. So this is a general overview over these simulations we are running now, and our idea is always, if somebody is interested to use one of these simulations, contact us, and we will always find a way how to join the data. So if you are interested, somebody want to do a project where you need a big multi-dark, dark matter only simulations, here is a bunch of simulations which can be used for this. And we are all in, almost all are already in Planck cosmology. The first, the Bolshoi, which I have shown you before, exists both in the WMAP5 and in the Planck cosmology. And these are a few test runs of a big simulation with different cosmologies if one wants to compare, if one wants to study the effect of the cosmologies. So PL means Planck.
Which is the time resolution between the snapshots? How many snapshots do you have?
It depends. We have for some of these we have a few hundred, 200 and something snapshots, like for small multi-dark. For others we have less. So there's no general rule for the small multi-dark and the new multi-dark. These two we have snapshot equidistant in log of expansion factor, because this is the best for the rockstar nurture trees.
Okay.
So normally we did it in different ways. In some of these simulations we have a lot of output in the region of the BOS data. For example, these are done for BOS analysis, and the mean BOS distance is something like 0.56 if I right remember, and redshift. And then we have around this number a lot of outputs in order to construct light cones for the observations. But for the ones where we want to construct a merging tree, and for the two one we have equidistant in A, in log expansion factor, and around 200 if I right remember, 200 beta. So this is about to give you an impression about the accuracy of these simulations. So the velocity function of Helios is basically the same as the mass function. So in the mass function you calculate how many objects you have in a certain mass range. In the velocity function you calculate how many objects you have in a certain range of the maximum circular velocity. So what is calculated is the maximum circular velocity, and when the distribution of those objects with respect to the maximum circular velocity. And the interesting question for everybody who is doing numeric cosmology is how stable are the simulations if you go from one simulation to the other one. So what we compare here is 1 gigaparsec with the 2.5 gigaparsec box, and with a much smaller one with a 0.4 gigaparsec box. And you see here that basically in this plot, which is a logarithmic plot, the lines are on top of each other. If you do a relative, if you compare it directly, you see that the difference is small. It's of the order of a few percent in particular. Of course, the difference at the high mass end is because of cosmic variance. And here you have a certain representation, and in the larger box you have many of these volumes, so the mean is smaller. But if you compare the part in the middle, it looks very well. It looks not that good if you go to subhalos. Subhalos is always a problem. I mean, this is again what we discussed yesterday or the day before yesterday. If you have a big simulation subhalos and you want to assign a property to a subhalo, it's getting more and more complicated. And this means if you compare when simulations, you don't compare in each case apples with apples. It could be apples with peas, or oranges or whatever, or in the worst case bananas, which have a completely different shape. So this is something you need to take into account if you work with these big simulations, and in particular if you work with different simulations. So this is the correlation function. Correlation function multiplied by R to the, what is this power? 1.
1.8.
1.8, yeah. And the full line is again in the big box, the dashed line. It's in the gigaparsec, the dashed line is in 2.5 gigaparsec box. This is the baryonic oscillation peak here. And this line, which is almost invisible here, I don't know whether you can see it, which goes until here. This is the linear linear correlation function multiplied by a factor of 1.3. And you see in this range the bias between the halo distribution and the linear correlation function is almost constant. What you see also is that the position of the baryon oscillation, the Barrow's peak, is constant, also is in the same position, but it is width changes here because this is changed by nonlinear effects, and this depends again on the realization what you have in the box on the resolution. So this peak, what you see here, I think you will have baryon oscillations. We will discuss it next week if I understand the program. So the peak, what you see here, is an enhancement of galaxies in a certain distance. The idea behind, this is a cartoon, this is taken from the Boswell page. The idea behind is that in the very early universe, if you have kind of density enhancement, then you have an enhancement of the density both in matter and in radiation, because matter and radiation are tightly coupled. And when the radiation, the sound speed of this coupled medium is almost the speed of light. It's third, the square root of 3 of the speed of light, and it's very large. And so if you have density perturbations, these perturbations go outwards until the moment of recombination. And the moment of recombination, the coupling between matter and radiation disappears because the electrons combine with the protons to atoms, and then the radiation goes away, and basically this density enhancement stays on the place and evolve further with the evolution of with the expansion of the universe. So you can calculate that this effect leads to a density enhancement, into density enhancement on distances of 100 and something, 107 or so megaparsec today. And yeah, but this is in a statistical sense. So this is a cartoon, you see you have many of these origins of these waves, and but if you do in a statistical sense an analysis of correlation function, that means the analysis of the probability to find at a certain distance a galaxy, this is enhanced here. And you need these kind of plots to compare that what you predict from theory with that what you see, for example, in the BOSS data, where you can measure the correlation functions of objects directly. So the next point, if you're interested in this big simulation, is the concentration of halos at different redshifts. The concentration of halos is an important property of these dark matter halos if you want to understand the galaxy formation, and it is defined as the relative is a ratio of the radius of the virial radius and the radius where you have an E and NFW. So you can define it in different ways, but this is kind of a rough definition. And then the question is, how does this concentration change with the mass? And this is a very well-known fact that it changes with the mass. So if you have lower mass objects, you have a higher concentration, higher mass objects have low concentration. The end of this curve is not very clear. So whether this goes straight like a line or whether there is some kind of an upturn here or not. And if you go backwards in time to redshift 1 or even to very high redshifts like 5.5, you see that there is a clear upturn in these concentration parameters. And there's an almost never-ending discussion in the literature whether this upturn is real or whether it is something which you see only in the simulations because of whatever numerical effects. So we see in these simulations a clear upturn if we concentrate our analysis to objects which are real, relaxed.
Excuse me, Stefan, at redshift 0, there is so few scatter, or the scatter is not represented here in this plot?
You mean this the scatter here in this?
Yeah, exactly, in consideration of different...
Yes, small scatter. So what is plotted here, you see the scatter, here you can see it very well, but here you see it, that the points are more scattered around this line, and the points are always mean concentration in a certain bin of masses. So the scatter, what you see in the bin, you don't see the scatter, it's not plotted here, but from bin to bin, you see the scatters in the less different points around this approximate line. So, coming back to that, if you find relaxed objects, and they are defined here as objects where, this is also something we discussed the day before, as objects where the center of mass and the highest density peak position are almost at the same position. The center of mass is in a different position than the highest density peak. You can expect that there's a second highest high density peak, and that this object is not very relaxed, and that you have a problem with in calculating the concentration parameter. Music. I showed you already the other music project, which was initially conditioned. Our music project, multi-dark simulation of galaxy clusters. So this was one of these clusters, and I showed you the movie before. And this is only a very short step in between now, because basically everything what I was starting yesterday to talk about are dark matter-only simulations. So in this case, we took an sample of the galaxy clusters about a certain mass, and we simulated each of these clusters with much higher resolution and full hydrodynamics. So the idea was to have a kind of mass-limited complete sample of galaxy clusters for statistics, and this is the music data set. We took for music 1 from a different object simulations, and music 2 is from these multi-dark simulations which I have shown you right now. As I mentioned already, pooling star formation is included in one with pooling and star formation in the non-relativity frame, and everything in relatively high resolution. So that we end up with a complete data set. It's complete over 10 to the 15, and it's 700 simulated clusters in over 10 to the 14. So this is a very large data set. You can do different things within the set. We have used it for studying of lensing, of cluster lensing, and we have used it also for comparing with observations. And this is one point. We have seen it also in one of the talks yesterday or the day before yesterday. It is extremely important to compare observational data and simulated numerical data in the right way. So this is an attempt to do it here for clusters. So this is a project of Veronica Biffy in Trieste, to take clusters from simulation, and she has written in software to observe these clusters as it would be seen by one of these X-ray satellites which observe clusters in reality. So this is an example how one of our clusters would be seen by Chandra. So this is colored according to the photon counts, and everything. The idea is in this project to observe these clusters really like real clusters. Of course, it's a completely different technique, because the information what you have in the simulation box is different of that what you have there. So you need to write. You need to take into account how to translate this dark matter plus gas plus baryons plus radiation in the plus temperature what you have in the simulation box into something that what in satellite you could really measure. This is the only way to get a direct conversion of theoretical observation and observation data. What we did, for example, is the gas fraction conversion with observations for a set of different clusters. So this is measured at different over densities. Most of the observations are at over density 500, and one can see that this fits pretty well with observational data. So now I come to the end of this. This was basically what I wanted to do yesterday. I come to the CosmoSim database at our institute. So this is a kind of advertisement session at the end of this talk. And CosmoSim database, the idea behind was to make as many data of our simulations available to everybody as possible. So we started with that a couple of years ago. We started with a similar technique like a Millennium database. Meanwhile, we have our more modern search algorithm, so everything should work faster now. Because one of the ideas in this database was to provide also access directly to the simulation. This is in principle impossible because one of these simulations is a few terabytes in some cases, and you cannot easily click on a database and get a few terabytes out of it. So the idea was to put the full simulation into the database and give the possibility to select part of the simulation, for example, in friends object or in certain volume around a certain object or randomly in the simulation, and get then all the particles and all the information from this object. This is a time-consuming procedure, and this is the reason why we developed further this database. Concerning the other data which are in the database, the main difference to Millennium is, besides the different box sizes, that this is blank cosmology, and Millennium is the old one with a relatively high sigma. So this is the results from about 150 million core hours, an equivalent of 70,000 years, gigabytes of raw data, terabytes of processed data. And this is distributed in archives in Munich. So we run our simulation in Munich, in Paris, and at the NASA computer in California. And for many of these projects, it would be very difficult to give you access if you want to have access. For example, it's almost impossible to get access to the NASA computer, and it takes some time to get access to Munich. So this is the places where we run it, and this is the idea behind to move at least part of this data in a central place, in this case to Potsdam, where you can access them. It's the first time here that I see sun. Now I don't. So it consists of different parts. The multidark is the largest part, or showing blank is somehow related to multidark. And clues are the constraint simulations, and we come to it later today, hopefully. We have friends of friends objects at different linking lengths, so one can download the full friends of friends objects, one can download the inner parts of it, so you can study substructures. With that, for some of the simulations, we have superclusters, so this is with a very high linking length. If you want to see whether these clusters are, the clusters of galaxies are connected into superclusters. For some of them, we have merging trees, and but not for all of them. We have spherical overdensity halos done with BDM, bound density maximum halo finder of Anatolia and Rockstar, the one I introduced yesterday of Peter Rossi. We have catalogs from these of halos and subpillars, we have profiles. So if you want to redo or to check this kind of density profiles, concentrations, like what I've shown before. And we started to put in merging trees. Here it says still coming. Meanwhile, this is a topic from March. Meanwhile, the first ones are in the database. I'm not sure whether they can be seen already from outside. And we have particles on a grid, so you can select these particles or particles as friends of friends objects. You can add more on request. We did not start to put too many particles in it because this is for us a lot of effort. And watch how many people are interested in that and how many people are downloading really particles. What we have right now is 31 terabytes of data plus another 14 terabytes of the index, which corresponds to 329 billion rows. We have 189 users, not so many so far. Millions of successful queries and terabytes of downloaded data. We looked into the distribution. This is what I added on top of it. I don't know, is somebody using a few Topcat? So you know, I mean, I don't use it. I use the IDL and all my own scripts, what I have. But many of the queries you can make in the database are directly related to Topcat. So you can go into the database and then you can say, okay, take something out and plot with Topcat, for example, the density of this, or plot this object, plot all the particles, or plot whatever. So I'm not one of these very active database users, because all what is in the database I have also in a different place, and I have my own experience in how to analyze and to use it. But so if you start to use a database, knowing Topcat and using Topcat is a very good thing. So this is how it is distributed. So we have people with more than 10,000 queries, we have more than 10,000 queries, we have people medium, heavy users. This is just to get a kind of an overview of how it is used, or how it was used last spring. Meanwhile, we have more in this region. And it is well distributed over the whole world, so you are here with quite a number of users, probably from Medellin, but also from other possible other places of the world. The volumes, what we have is multi-dark. This is basically everything is multi-dark. I mean, Bolshoi is a bit, Bolshoi P and Bolshoi have different names, but they are part of this multi-dark. And the cruise so far is very small. The cruise contribution of the constraint simulations is very small. By two reasons, the simulations are much smaller, so you cannot produce so many data. And we also only started to put something into the database, and again want to know whether people are interested to use it or not. So, what I hoped to show you is that this kind of numerical simulations is a very useful tool. You need numerical simulations if you want to observe, if you want to understand large-scale structure. So these numerical simulations are necessary for the interpretation of, for example, of observational data on large scales. And without numerical simulations, even if we could not make many predictions, for example, which later can be found, but without these numerical simulations, we probably wouldn't have understand the evolution of structure in the universe at all. And the databases are important. These are important tools which become more and more important in the analysis of large-scale simulations. And I think there's plenty to do for the next generation of astrophysicists. And I want to go now to small-scale structure. such, you might think a little bit whether you want to do something. In large-scale structure. I hope it is correct. You never know. At least I never know whether it's correct. I even don't know it in English. I know it is in German correct. But okay, so now let me find. So the idea was to talk first about large-scale structure formation and then about small-scale structure formation, because this is kind of different. It's kind of different way to look on the structure formation. So after my experience of yesterday, I have tonight heavily shortcut. So what I want to show you is basically to give you a rough idea about what we are doing with small-scale structure formation and to be ready before our friends come and want to make a photo of us at 10 o'clock. So I think I can make it. Maybe we will finish even earlier now after this cutting. The formation of small-scale structure. Small-scale structure is very interesting, in particular in the nearby universe, because of course the further you look away, the more difficult it is to see this small-scale structure. And what we basically did here is to study information of small-scale structure in the near universe, which one calls from time to time near-field cosmology. And the reason is simple that, as we discussed the days before, if you do simulations of the universe, if you study the universe, you need a very big volume. So the representative volume of the universe is probably 500 or even more megaparsec, depending on what you want to study. And on the other side, you want to have an extremely high resolution. It should be at least the order of 100 parsec, better higher, which makes immediately a problem on present and also on future computers. Then the mass range of the objects you are interested in goes from, the most massive objects are above 10 to the 15, and the smallest objects are around 10 to the 8 in dark matter or smaller. And if you want to resolve this with a reasonably large number of particles, 1,000 particles, you get orders of magnitudes of particles in this simulation, which is again completely impossible, at least on the present computers, and probably most probably also not that easily possible in the next generation of computers we discussed yesterday. And then the third problem is that present-day observations and also future observations will be more accurate the more nearby you observe the universe. So an outcome of this idea and the idea of near-field cosmology is to look into not into a representative volume of the full universe, but to look into something which is next, which looks like the neighborhood of our Milky Way. And then the question is, how can you do this? How can you simulate the neighborhood of our Milky Way if you know only how it looks today? And this is the basic idea behind this cruise project which we are running in Potsdam and Madrid with Caballeros and in Israel and Hebrew University with Yehuda and many others, observers from Lyon and Hawaii. So included into this project. And the idea is to run simulations of the universe, and in particular simulations of the very local universe, namely the local group. And this is one of our simulations, just to give you an idea how it works. So you have a simulation in dark matter only when you do resimulations in full hydrodynamics, and when you identify in these simulations objects which are on the position of the Milky Way or Andromeda or M33. And when you have, this is a zoom, I mean this is a dark matter only simulation, this is a zoom into the hydrodynamical simulation at the same position. And then the idea is to study the formation of these objects, of our freely observed objects, in the right environment. Why are we interested in this constraint simulation? As I said before, we know our environment pretty well. We knew it already in 1993. This is about the Faxen, and we know it even better today. So we know that our home galaxy has been formed in the neighborhood of a cluster of Virgo, and there are other clusters around us. And we know quite well the properties of all these clusters. So it's a good idea to study the formation structure exactly in this environment. How do we do it? We did it in different ways. How we do it now? Now we use cosmic flows data. Cosmic flows 1 and 2 is a project of Brentali and Gottloeber and many others. The idea is to measure the position and the velocities, the radial velocities of galaxies in our neighborhood. And so this is the Cosmic Flows 1 data. These are about 2,000 data, 2,000 constraints. And I come later to point how we use these constraints. But for the moment, the situation in here and here is we have 2,000, or in the new data of 2013, 8,000 constraints, and constraints are for us positions and radial velocities of galaxies. You know that we don't see anything in the zone of avoidance, in the plane of the Milky Way, so we don't have information in these regions, but we have plenty of information in the other region. And you see already here that the further you go away, the less information is available. So you have nearby, many nearby information about the distribution of galaxies, but not so much in the distance. The main difference between Cosmic Flows 1 and Cosmic Flows 2 and Cosmic Flows 3, which will come out in 1 or 2 years, is the number of objects and also the accuracy with which you can measure these objects. So how is it done? This is again this catalog. And you observe a certain redshift, and you know that this redshift comes from a distance and the peculiar radial velocity of a galaxy. And if you have the brightness of the galaxy, and the observed one and the real one from photometry or from some calibrations, mainly these are Tally-Fisher luminosities, then you can calculate the distance of this galaxy. So you know the distance and the redshift, and you can calculate the peculiar velocity. So this is the main idea of this Cosmic Flows catalog. You can immediately see that you can expect quite big errors in this radial velocities, because this is the redshift you know pretty well, but the luminosity, the brightness of these galaxies you know also pretty well, but the real one from the Tally-Fisher relation, for example, from the measured rotation curves of these galaxies is much more difficult, so there will be a lot of errors in it. So at the end what you have is a set of observational data, probably with large errors in in the distance, because this is what you calculate from the velocities. Now you have this today, and you want to go back somehow to that what is the input some 30 years away. So how do you do it? So you have a radial regular velocity, and you use a Wiener filter algorithm. This is something what Yehuda has developed. And the idea behind is that you calculate basically under the assumption that you have a cosmological model, and under the assumption that you have something observed, radial velocity observed, you calculate the expected 3D velocity of this object. If you have it, you do the next step. Now you have information about an object in a certain place, and you ask yourself, where does it come from? Because the initial condition, I mean, you know that our galaxy or us, we have not been formed here in this place, because the galaxy moves with a relatively high speed over the last 13 giga-years towards Virgo, so it has been formed somewhere far away from the place where we are now. So this is an attempt to calculate this place simply by doing in reverse Zeldovich approximation. That means doing the same what is normal Zeldovich approximation, but in the other direction in time. And at the end of all this procedure, you get a point in the initial conditions where you have a constraint, namely a constraint that something has been formed in this place. How does it look in the initial conditions? In the initial conditions you have, first of all, a kind of an random field, which is a representation of the power spectrum. So this is this almost invisible one here. And when you come with this constraint and say, yes, but I know that at a certain position, this is not a power, this is not the power spectrum, this is a density or velocity field here in this case. But when you know in a certain positions, you have a constraint, and you put this constraint into this position, and then you change correspondingly the underlying field, and you get with these two constraints out of the original field mu1, which has now in these two places the right value. So if you go back, you have 8,000 constraints now for the new cosmic flow 2 data, and this will be reduced this has been reduced to about 2,500 constraints, because if you have a cluster of galaxies, you cannot use all these positional velocities. This would be a nightmare because of the finger of God effect. So what you are doing, you group objects which are in one place, you group them all together and take a mean position and the mean velocity. This reduces all that stuff to about 2,500. And you have, in a typical simulation, 500, 1,000, 2,000 cube particles times, you can calculate how many initial conditions you have, and only a handful of constraints on them. Nevertheless, this works pretty well, and you get, if you do this procedure, and here in this place I want to mention that this is a PhD thesis first of Timo, who was a student in Potsdam, and then of Jenny, who was a student in Lyon, and is now a postdoc in Potsdam, and she's doing all these kind of initial conditions and running the simulations now in Potsdam. If you do this, you end up with something like that. So this is a simulation we have performed many, many years ago. We can do it now much better, but this illustrates it pretty well. What is the attempt of it? So this is a big box, and we have in this big box Virgo and the great attractor and Coma and Perseus in the right position, and somewhere our own galaxy here. And if you do the same in the smaller box, you can see again that we have Virgo here and we have Virgo here. And now the interesting is, if you compare these two, this is now not anymore assumed simulation, but this is something where you have used the information about constraints, and actually this is something what I expected has been done in this project with Sabine, but I don't know whether it has been done, because the big box now is periodic and the small box is also periodic. But with its constraints, which we put into the initial conditions, we force basically the big and the small box to have the same object and the same position, and without doing the zoomed simulation. So this is in principle possible, and there's no error here in the initial conditions, in the periodicity. Or these boxes are from the very beginning normal periodic boxes. The price you are paying is you don't get it exactly. And this is the price you are paying with all these constraint simulations. You have only a handful of constraints, you cannot expect that you get exactly what you observe. And if you compare these two, you see basically the differences. So we have these two objects here, but it goes in a different way. And I mean, this is not very visible here. But anyway, if you look only onto this part, you get already an idea that it is different. And then consequently also the evolution is slightly different. And when you do the next step and you go into the place and you look whether you have something like a local group where, and you find always some kind of a local group. It will be in the right place or slightly shifted. Again, the problem is that the local group is an object of the size of a megaparsec roughly, or 1.5 megaparsec. This is highly nonlinear, and you cannot expect from the observations that you get this highly nonlinear object exactly at the same position. So if you do all these kinds of constraint simulations, we find local groups, we can run local group simulations. We are in the right environment in the sense that we sit in the big box or in the small box in the right position, and we have the right type of fields from the other objects far away and the right interaction over the full merging history, but we are not exact in representation of that what we observe. So with this information we run a sample of local volume simulations first of all, and we were interested in these local volume simulations and about small scale structure and how does it look if we introduce warm dark matter. I mean, until now we were talking only about cold dark matter simulations, but the question is if you go to small scales, there are a number of problems you probably have heard about, and one of the solutions could be warm dark matter. The problems I mentioned is, this is an old plot from, at least 10 years ago, I don't remember exactly from when, is this missing satellite problems. This is the fact that if you look into any of these simulations I have shown you, you see a huge number of small objects in clusters, and if you remember that the power spectrum is almost scale-free, then you would expect that you see the same huge number of small objects in something like a galaxy. So a typical cluster has hundreds or even thousands of galaxies, and from the point of view of the dynamics, this is basically the same as only dynamics is basically the same as a galaxy. So you see in a cosmological simulation, as expected, many small objects around the galaxy. On the other side, you know from our galaxy that there is a handful of, you have big hands, 50 or so now, satellites, but only a handful very big ones. So this is one of the questions, and a simple solution is if you introduce warm dark matter. So the basic idea of warm dark matter is that the matter is not cold, so it has a kind of free streaming in the early universe, and this means that this, due to the velocities in the warm dark matter component, the small scale structure is erased. And if you translate that into a power spectrum, this is now the power spectrum what we have seen before, it looks like that. And now we have multiplied it by k to the 3, so it looks like that. This is the dark matter only power spectrum, and introduction of warm dark matter means cut off at a certain length, and this length depends on the property of the warm dark matter. So there's a direct relation of the property of an elementary particle and the power spectrum what you see in the universe. So with that, we can run simulations. This is very old. We did it 10 years ago, which can be seen in the normalization. This is in WMAP3 normalization. And what did we find? So if you compare the cold and the warm dark matter scenario, you see Virgo at the same place and our local group at the same place. And basically it looks more or less completely identical, which is necessary because, as I said, the warm dark matter makes differences only on small scales. So you can search here for something like that maybe, which looks different to what you see here. But on large scales and on the size of the box, or compared with the Virgo cluster and the local group itself, it must be identical. If you go now to smaller scales, to the local group, then you see the differences, complete differences in the evolution of different objects. So you can see already here that for a large galaxy, it's one of the main galaxies in the local group simulation. The gas distribution in the CDM1 and in the BDM and warm dark matter is completely different. Here you have a lot of substructures which just run here. And the same on the other side, if you look in the stellar densities, you have here more substructures, and it's not so clearly visible in the stellar densities as in the gas densities in this plot. So this is that. No, I'm not sure. No, yeah. I was not sure whether there is a movie behind. So this is the very nearby universe. Now we look into the not so nearby universe, and this is a simulated sky map. So the Virgo and Fornax in the right, more or less right positions, and the dots are now halos with relatively low masses, about 5 times 10 to the 9. So you would expect to see differences also for these halos in the distribution. How can you measure it? There was a project where I think radio telescope, it was called Alpha, and this is a survey of galaxies. And what we are doing now, we compare basically in our simulation, we select for a given observer sitting in the right position of the local group and looking into the direction of Virgo and looking into the anti-Virgo direction again from Virgo and measuring velocity function, again the velocity function. So basically the number of objects above a certain circular velocity, which can be translated into masses as we have discussed before, compared with observations. The observations are here, and this is the dark matter, and this is the warm dark matter. This is cold, and this is warm dark matter. And you see that in this simple run shows you that warm dark matter better fits the observational data than cold dark matter in this region. You cannot say anything about this region. This has to do with numerical problems. So there are 2 lines basically here. You can more or less believe maybe to this line, and this is a line which you can calculate from numerical simulation, where you would expect. So left of this, you cannot believe in anything because you expect a huge number of fake objects and starting at this position. And this is also what you see here. You see here fake objects increasing, and this is simple and numerical artifact. But we kept it in the plot in order to show that we believe in the region right of this line. And right of this line, there's pretty well match of the observational and simulated data under the assumption of a certain warm dark matter property. So from this point of view, you could see that warm dark matter is a good candidate to solve, for example, this problem, the discrepancy between these observations and predictions in call it dark matter. Another very local problem is the number on the spectrum of voids in the local volume. So if you go into the local volume, you see, as in big volumes, that you have many places where you see dwarf galaxies, and you have other places where you don't see dwarf galaxies. So there's a void in the distribution of dwarf galaxies, and now you can study the statistical properties of this void. This has been done in a paper of Gottloeber in 2009. On this side from the cold dark matter scenario, and the basic idea of this paper is I'm measuring the distribution of these voids, I'm measuring the size of these voids, and I compare it with simulations, and then I can see that the observed distributions can be fitted by observational data if I assume a very low circular velocity of 20 or so on this range. So from that point of view, everything is okay. But now, if you compare now directly of 35, sorry, if you assume 35, you can fit the data. But if you compare it now directly with observational data, you see that this circular velocity is by far too large. So the observed galaxies have 20 or even smaller circular velocities. So this means the prediction from the theory would be somewhere here, and is in strong contradiction with that, what you observe. If you do the same game, and this is something what Stefean did with our simulations, with one dark matter simulation, it fits pretty well. So you see that with 15 and 20 kilometers per second, you can fit the observational data, and so you are happy, and you could come to the conclusion, okay, I need one dark matter model, which is good because you have found something interesting. But then you go the next step. So this is what I said in the first time, and then you go the next step, and you look into all these halos, the halo evolution, and then there is a critical point. If you look into the halo evolution, you need a certain mass in the early universe in order to form stars. If these halos are not massive enough, you cannot, the potential is not deep enough, but basically you are losing the gas and you don't form enough stars and you don't form galaxies at all. And this is something kind of complicated, a lot what we did here. But the main idea is this is the evolution of the halo mass. You have halos which are looking into going in this direction. They start relatively massive, and then you end here, and then you have other halos which increase more. And you can show that in this region, right of this curve, by the background radiation, the gases expelled from these galaxies. So basically, you stop star formation if an halo is going to cross this line. So this works pretty well in a cold dark matter universe, but if you do the same game in a warm dark matter universe, you are running into problems. You don't see enough galaxies which have really, you don't see enough objects that have enough time to form stars, in particular in the very early universe. So if you combine all that together, you see, well, I can explain the distribution of objects in the warm dark matter model pretty well. I'm going to run into problems if I try to explain the formation of early galaxies. So this is something to demonstrate you that one result alone, or two results, what we have shown with this distribution, or solving one problem under one assumption is not enough. And if you make a new assumption like warm dark matter, you must check it against basically everything. And this means also against the formation of the early objects or of enough low mass galaxies during the evolution of the whole universe. So from my point of view, my conclusion concerning warm dark matter is, in the moment, yes, it is an attractive possibility to decrease the small-scale structure formation, which goes in the direction you want to have. more problems with early universe and galaxy formation, so that probably this is not the right way. Local group simulations. So we made a bunch of local group simulations, basically assuming a box of 64 megaparsec, finding the local group, doing a sphere of 2 or sometimes 7 megaparsecs around and simulating it with different resolution. So the resolution in gas was 10 to the 4, and the best resolved simulation in force resolution of 150 parsec. And you see the same structure what I have shown you before. And now you can look. So this is again, this is again not very well visible. This is a Milky Way and M31, as you see it in the dark matter distribution. If you go to the gas distribution, you see the same objects, but now it's much smoother. Of course, you have in gas much less knots than you had in the original dark matter distribution. And then we are flying towards one of these galaxies, and it's M31 in this case. And then you see that the gas distribution is flat. This stuff more nearby you are coming. You see disk, and next we are flying around this disk, and you see the problem I mentioned before, that you have the disk structure, but around this disk you have plenty of gas clumps, more than you would see in reality. So this is now again called dark matter.
So is it color-coded by temperature density, or what is it?
This is color-coded by the gas density. Full gas density. This is the gas evolution. This is another movie showing you the evolution of this gas with time. The interesting thing is info here, and that for some reason it jumps always to this beloved back. Okay, when you can study the info of satellites, and one of the reasons why we did this is this info of the mass evolution of the M31 and of Candida. But what I wanted to show you from this page is the info of these galaxies. And the interesting thing is here that these are the two main objects, and these the colored are the objects which end up in the lane. And you see that we have here an interaction with one of the main objects, and then the satellite is flying towards the other side. And we made this test, and we started with because there were claims in the literature some years ago that the Magellan clouds have interacted before with Andromeda. We wanted to see whether we can see in our simulations this behavior, that we have satellites, informing satellites, which interact with some other galaxies. And doesn't go from us now. Another thing what we studied is the pattern, the tidal streams of satellites. So this is an example at redshift of 4.8. So if you look into observational data, you see that you very often can find in tidal streams of stars observed in our galaxy. The more and more observation we have of the galaxy, the more these tidal streams of earlier interactions you can see. And one of the ideas of this brought for us to see whether we can see something like that in the simulation and how the different components are related. So this is the full picture, this is the gas picture, this is the stellar picture, and this is the dark matter only picture. And in all cases, you can identify this path of the objects if you follow the streams. You see it best, of course, in the dark matter, and it's most difficult in the stars. Also because for the object, for the infalling object, the stars are more concentrated, and you need to be more nearby to the center of a massive object in order to remove stars from the by tidal forces. And the gas, the dark matter and the gas is on larger distances and it's earlier removed, and the gas is removed in addition by air pressure. Another thing what you can study in these simulations is the infall from a certain direction. This is again work which is going in the direction what Yehuda is doing, so I'm not sure whether Yehuda was talking about the cosmic web, the pure, so he mentioned it at all or not. But what we see in reality and what we see in simulation is that it looks like the galaxies, the satellites of the galaxies are distributed in a certain specific way. So there's the idea that these satellites are in planets around Andromeda, Bata paper, and what you see here basically is the two objects, Milky Way and M31, and the relation to the logo. And then you can measure in this simulation whether these satellites are coming from all possible direction or from a specific direction. And the plot on the right-hand side demonstrates that we can in fact from a very specific direction on the sky. So this now I covered too much of my talk because this was already my last plot. What we learned when doing all these simulations, the more you are talking about this simulated real universe, the more people are approaching you and asking you how exactly can you simulate the universe, how exactly can you simulate whatever is around the local probe. And once also the planetarium in Chicago approached us and they asked us for data from our simulation to show in the planetarium the neighborhood of our galaxy. And this is really impressive. I saw it once. So these are two persons standing in the planetarium in Chicago and watching one of our simulations, whereas in the background is some kind of music and some kind of explanation that this is what you see. So if you are doing this kind of large-scale structure, and you are talking about objects which are billions of light years away, nobody is really interested in this. If you are talking about our neighborhood and this, we see that there is a large interest from the public, from popular science, and so many people will approach you and ask you, can you explain it in more detail? Can you show it where we came from? And another example of that is the success of this Landia-Kea paper, what Brentali and Buddha and others did. It's also an attempt to explain the local universe, and we are running now simulations where we see the same Landia-Kea in our simulations. So now I'm ended with that. 20 minutes too early, but these are the 15 minutes that I have stolen you yesterday. So I could have, maybe I should have cut it less. From this I have taken away the whole stuff, what we did in the interaction of satellites with the cosmic web. I mean, I can tell you a few words about this. This is a PhD thesis by Andro in Argentina. So he did a very interesting PhD project. So he was looking into our simulations and identified in this simulation satellite galaxies which are moving with relatively high speed with respect to us, with respect to the local Gottloeber, with respect to the Milky Way, but far away. And the problem, you know, from galaxy cluster, this is very well known, that if you move, if the galaxy is moving into a galaxy cluster, when the outer parts of these galaxies are simply removed by lump pressure. So you must imagine you have a gas and it flies through the center of this galaxy cluster, then you have a naked galaxy basically remains. What he identified is something what we call cosmic web stripping. So if you have a satellite galaxy which moves with a very high speed through the cosmic web, through a low density cosmic gas web, and it happens that it moves through it by chunks, more or less perpendicular through the cosmic web. And when the low density cosmic web and the high speed galaxy together lead again to stripping. So what he's found in this simulation is that you have satellite galaxies which are far away of the local group, moving very fast and lost at some moment completely by gas. So he has plots showing this. You have an evolution of a dark matter, so it's increasing all the time, the dark matter. And you have an evolution of the stellar content of these galaxies, which increases all the time and suddenly it stops. No star formation after a certain place. And then you look into the gas evolution, gas content evolution of this galaxy, and you see that there's a lot of gas in this galaxy and suddenly it goes down to almost zero. Then you go into the simulation and check why it happens. And if you go to the simulation, you see that it happens in the moment when this satellite is moving through a more or less dense filament of gas and is losing all its internal gas due to this pressure interaction. And at the end, it's more or less naked. It doesn't form more stars. And this is interesting because it solves basically the same problem what the warm dark matter would have solved on the basic of dynamics. So warm dark matter would tell us that we don't see enough, we don't see so many small scale, small low mass objects because they have never have been formed. And this scenario says there are a few of these objects which have the right mass, but we don't have so many stars inside because we lost at some moment their gas content, and we lost it without interacting with one of the main galaxies, which is easily to expect, but we lost it somewhere in between. This is an interesting, very interesting result of this PhD thesis, which he defended 2 months ago. So unfortunately, I cut it all right in order to be sure to finish.
But you can upload it.
If you want to see something from it, do you want to? Then I can find another talk included.
Okay, not now, I think.
Now?
No, not now.
Okay. I have talked enough. So I would prefer you ask me some question if you are interested in it, instead of running through all my talks and finding the talk in which I talk about this part. Questions?
Well,
you talk about the missing satellite problem on your slides. So what do you think about the Illustris simulation? They claim that they solved this missing galaxies.
And they claim that we solved it basically also on the basis of bionic physics. I don't know which. I mean, we claim that we solved it. Point. To look into the details, how, where, why it happens, I don't know whether we looked as much into the details already or not. I mean, from my problem, or my experience with all these simulations is, if you look into the distribution of stars and of galaxies in some moment, you see always something. You see, for example, I don't have too many satellites, or I have too many satellites, or whatever. The problem is to understand why it happens so. I mean, from a dark matter halo, they are there. If you don't see them, it means at some moment they have not been formed. And the stars have not been formed in these halos. And then you need to identify why. And, how it works in the Jerusalem, I don't know. I never had a look directly into these simulations, but as I said, I mean, this was the whole idea of showing you this warm dark matter part. And sometimes you can solve a problem easily, but it is not a real solution. The real solution is in that case probably bionic physics, as we have seen in our example, and as the hydrodynamically illustrated simulations have seen. It could be also a problem of the code. Again, I don't know.
So just understand the last scenario we're mentioning, so these are small satellite galaxies that their gas are stripped because of the interaction with cosmic wave before they unfold to a final structure, let's say. So, but there is still enough time to form a bit of stars before this.
Before, yeah.
Okay, so the point is, this scenario would alleviate the missing satellites problem in the sense that these small satellites still would exist as dark matter superhalos, but with so few stars that they are very hard or impossible to be observed.
This, I mean, the interesting, why we were interested in this particular problem is that these galaxies never reach us. So we stay away from, we don't become satellites of the Milky Way, but they are dwarfs in a distance of 1 megaparsec, between 500 and then 5 or 2 megaparsec of the Milky Way. They never interact with one of the big stars, nevertheless lost their gas. And this would more help to explain this void problem, what I have shown you before, the void spectrum what Anton Tikhonov has measured. Because this is also for the illustrators, I don't know what we exactly did. It's two different problems to reduce the number of observed dwarfs, for example, far away, non-interacting with massive galaxies, and the other problem if we interact with massive galaxies, then it is easier.
Local group simulations are publicly available?
More or less. They are publicly available in that, and this is respect that if anybody asks us to access to the data, we always give.
Can you please
if you come with a project, if you say I want in this kind of simulation, I want to study this or that, we find the way to get access to that simulation.
Can you please remind me what is the mass resolution of this simulation of the local group?
The ones what I have shown you in dark matter mass was 2 times 10 to the 5 or 3 times 10 to the 5.
Any for the bargaining components?
For the gas mass, it's then a few times 10 to the 4. I mean, the way how we do it, we split, it depends again on the code, but you can do it in Gadget in different ways. But we do split in the process of gas formation each gas particle into stellar particles. So that means if you have a given mass resolution in dark matter, then you can calculate 15%. Also you can say this is 85 is dark matter and 15% is gas, so you get a factor of 15 divided by 85 divided by mass of the particle. For the gas particles, and then the stellar particles are half of that. This gives the resolution about a factor of 10 better in stellar particles than gas particles.
And small galaxies that you find in this simulation, there is some of those galaxies with nice disk morphologies, you could say, or?
Now, in the newer, yes, not yet in these simulations. The old ones, I mean, this is a problem of galaxy formation. You have two problems. You have one problem is we are doing it with this cruise is putting the galaxy in the right environment when you are running your galaxy formation code. So as long as you are talking about these infalling satellites or these structures on the scale of a few megaparsec around, you have it more or less under control. If you go to the galaxy formation itself, the result still pretty much depends on the code you are using. And there was this big compilation project led by Cecilia from our institute. Cecilia is kind of big one. There's another one, I don't know who's the head of, who's leading it, but it is connected to Joe Creamer and his group in Santa Cruz. And well, the main result is we have a rough idea how galaxies. This is something what I see as somebody who is not running by himself specific galaxy formation simulation. Somebody who runs this simulation would see it more positive. Probably, from my point of view, we can say that we have a rough idea how it works, but we don't understand it in details. So we have plenty, for example, the good results you find always in I think at some moment they stop the cooling for a few time steps. So this is something which there's a good reason for doing it. But if you do something like that, it is beyond any. This is an experience. If you do that, and you have a reason why to do it in this way, then you improve your results. But it doesn't mean that this is the physics which really.
I was asking that because I have an idea I would like to work on, but I would need some. Because these galaxies, not to understand galaxy formation, just to have a distribution of gas that was formed or assembled in a realistic cosmological environment to interpret, to extract rotation curve in the observer's way and to analyze them. For example, to calculate the dynamical mass for the rotation curve for systems that are not perfectly in equilibrium, or to see how the observer rotation curve would depend on the inclination dependent of the sky, etc. But in that case, what they just need is disk-like for morphology and high resolution in gas, because otherwise I cannot reconstruct rotation curve in the first few kiloparsecs. But
for the simulations we have from local book, the methods are in the code with this by Cecilia. So we can talk about that later on, so you can contact and try to get something, but I'm not sure whether she has already seen a solution either. This is something you need to discuss. You need to discuss it. Getting these the old simulations from us is not a problem. It's not we can get it at any time, but if you want to study with this for what is this good. So guys, I expected you, so I cut it yesterday night. A substantial part of my lecture with the result that I was ready already 10 minutes ago behind the question session. So